Welcome back to this course on multi-core architectures. In this final lesson in this module on memory consistency, I will briefly describe more relaxed memory consistency models than sequential consistency. These relaxed memory consistency models allow more hardware and software optimizations than sequential consistency does. Bottom line, sequential consistency needs to maintain all memory access orderings. Write, then read, write, then write, read, then read, and read, then write. In other words, sequential consistency is very strict. The question now is, can we relax some or all memory access orderings? Does this also yield a programming model the programmer can work with? What about relaxing the write then read order, allowing a read to bypass an earlier write, provided of course they access different addresses? This would be a very important optimization since reads are often on the critical path. The processing core is waiting for data while writes can be handled in the background. Two memory consistency models relax the write then read order. They are called total store ordering and processor consistency. To think about whether relaxing the write then read order makes sense, consider this example that we have seen several times before. Event ordering using a busy waiting loop. Will this code still work? Correctly if the write then read order is relaxed and print the value 1? I give you 5 seconds to find an answer. The answer is yes, the code will still work. Since thread T0 first does a write and then another write, and their ordering is maintained, while thread 1 does a read and then another read, or read until the flag is set and then one more read, and the read then read order is also maintained. The other example that we have also seen before, mutual exclusion using warning flags. Initially both warning flags are set to 0 and then both threads set their warning flags and then check each other's warning flag. Will it still be impossible for both if statements to evaluate to true? Again, you're given 5 seconds. Unfortunately, the answer is no. This program no longer ensures that both threads do not enter their critical section at the same time. Both threads first write their flags, their own warning flag, and then read the other thread's warning flag. Because the write then read order is no longer guaranteed, it may happen that the reads are actually executed before the corresponding writes, which implies that both threads will think that it is safe to enter their critical sections. To conclude, relaxing the write then read order enables a programming model that enables some synchronization constructs, but fewer than sequential consistency, while it allows some optimizations to be performed either in hardware or software. Besides relaxing all or a few memory access orders, are there other memory consistency models that programmers can work with? For example, all interesting parallel programs need to synchronize. Does this allow an intuitive programming model? Such memory consistency models are based on the following observation. Different data can and typically do have a different purpose. Consider this by now well-known example, event ordering using a busy waiting loop. We can see that flag on the one side and A and B on the other side have a different purpose. Flag is used for synchronization, while A and B are data that need to be communicated between the two threads. And we can, in fact, reorder the data accesses. It doesn't matter if A is first set to 23 and then B to 37, or vice versa. Identically, it doesn't matter if thread T1 first reads B and then A, or the other way around. In all cases, the result will be the same. Memory consistency models based on this observation need to distinguish between data accesses and synchronization operations. Hardware and/or software can then freely reorder data accesses, while synchronization operations must be executed in a sequentially consistent manner. In fact, synchronization is needed whenever shared variables are written by one thread and read or written by another thread, whether or not multiple copies exist and irrespective of the memory model. A situation where there is no synchronization between writing shared data in one thread and reading or writing in another thread is called a data race. It is called a data race because the outcome is unpredictable and depends on the relative execution speeds of the different threads. In the past, there have been bugs in critical software that were due to a data race, and some of these bugs had catastrophic results. For the same reason, programs that are well, meaning 100% correctly synchronized, are often called data race free. If the hardware implements a memory consistency model based on synchronization, the programming model should enable or force the programmer to declare shared variables used to synchronize as such. For example, using a special keyword sync. Then the hardware only has to enforce the correct ordering of memory accesses to variables declared as sync. Other memory accesses may be freely reordered using all the techniques we know from single core technology. Here's our example again. The only modification that I had to make was to declare the flag variable as a sync variable. This seems to be a reasonable burden to be placed on the programmer, since the hardware will become a lot faster. In fact, there are two memory consistency models based on synchronization. The first is called weak ordering. In this model, accesses to non-synchronization data must abide the thread order dependencies when accessing the same address. Otherwise, there is no requirement. Not even coherence is a requirement. Furthermore, variables that are used for synchronization must be declared as such in the program or accessed using specific statements. In addition, accesses to synchronization variables must be recognizable by the hardware at the instruction architectural level. For example, we must use read, modify, write instructions when acquiring a log and use a special store when releasing a log. So we can no longer use a normal store to release a log as we did before. Finally, the hardware needs to enforce the following ordering: synchronization access, then read or write then synchronization access, and the accesses to synchronization variables need to be performed in thread order. Normal reads and writes can be freely reordered. The second memory consistency model based on synchronization is called release consistency. This model is even weaker than weak ordering. It distinguishes between acquiring and releasing a log and exposes even more parallelism in the memory system than weak ordering. This concludes this lesson. I hope to see you back.